Have you ever actually stopped to think about how the everyday apps on your phone or the massive operating systems running your computer are really built? I mean, it's so easy to picture just one solitary genius typing away in a dark room somewhere. But in reality, constructing modern software is a whole lot more like building a massive digital skyscraper. It takes incredibly precise blueprints, highly specialized construction crews, and just rigorous safety inspections. So today, we're going to demystify that whole entire process. Welcome to our explainer on the architecture of software. Okay, here's our blueprint for today. 1. Decoding software engineering. 2. Meet the development team. 3. The development lifecycle. 4. Agile versus waterfall. And 5. Testing and documentation. Let's dive right in. So, to set the stage, there's this really striking quote from David Parnas. He says, "All software engineers can program, but not all programmers can engineer software." And that just hits the nail on the head. Writing a few lines of code to make a computer do a neat trick, well, that's programming. But designing, writing, testing, and maintaining complex systems to reliably solve problems for millions of users, that is engineering. It's literally the difference between tossing together a wooden shed in your backyard and engineering a 100-story high-rise. All right, let's start at the very beginning with Section 1, Decoding Software Engineering, the Foundation. The Bureau of Labor Statistics actually has a really fascinating definition for this. They define software engineering as the systematic application of scientific and technological knowledge, methods, and experience to the design, implementation, testing, and documentation of software. Now, the absolutely crucial word there is systematic. As researcher Pamela Zave pointed out, the whole purpose of software engineering is to control complexity, not to create it. Software engineers aren't just staring at isolated lines of code. They have to look at the entire system's stability, how all these different programs talk to each other, and how the whole shebang is going to be maintained over time. So who actually puts on the digital hard hats? Section 2, Meet the development team, the construction crew. Pretty much any modern development team has this leadership spine made up of 3 distinct roles, and honestly, they get confused all the time. First up, the engineering manager. They're looking at the big picture, end-to-end delivery and scaling the team. So hiring, coaching, and cross-team initiatives. Then you've got the tech lead. Their main obsession is code quality and architecture. These are your senior developers with deep stack expertise, and they're mentoring the rest of the team on the actual tech. And finally, the team lead. They're the ones in the trenches, focusing on workflow and coordination, allocating work, and handling the daily operations for a single team. Working together, these 3 roles keep the quality up and the team motivated, even under crazy delivery pressure. But of course, the leaders are just part of the story. You also have the product manager, who's kind of like the quarterback driving the strategy. The product owner, making sure the end users actually get value out of it. Need someone to turn that big roadmap into an actual schedule? That's your tech project manager, bridging the tech and business sides. You've got the software architect crafting the system design, and the software developers, the literal wizards who bring the code to life. Oh, and you can't forget the UX and UI designers, ensuring the product looks gorgeous and actually makes sense to use. Finally, the QA engineers who act as the ultimate quality shield. Every single person brings a highly specific superpower to the site. All right, so we know the who. Let's talk about the how. Section 3, the development lifecycle, the blueprints. Take a look at this cycle. Notice how it's a circle? The software development lifecycle, or SDLC, isn't a straight line where you just finish writing code, brush your hands off, and walk away. It's a continuous, repeating loop. It's completely designed to enhance quality and adapt to what users need over time. Basically, it acts as the master blueprint to minimize rework and hopefully get it right the first time. Let's walk through this step by step. Say your favorite social media app wants to add a brand new video feature. Step 1 is always requirement gathering and analysis. The team figures out exactly what this feature needs to do and writes it down in a software requirement specification, or SRS. Step 2 is design, where they map out the architecture. Step 3 is development. That's when fingers hit the keyboards and the actual code gets built. Step 4 is testing, where they check the code against the SRS to squash any bugs before you ever see it. And finally, Step 5, deployment and maintenance. The update hits your phone, and then the team continuously monitors and tweaks it over time. Now, to get through that life cycle, you need a solid game plan. Section 4, Agile versus Waterfall, Project Management Showdown. Okay, so there is a massive difference between these 2 philosophies. Waterfall is exactly what it sounds like. It's a strict, step-by-step, sequential flow. You have a fixed scope and do all your detailed planning right up front. But because of that, making changes later on, super hard and really expensive. Agile, on the flip side, works in cycles, broken down into short little bursts called sprints. It absolutely thrives on continuous feedback, so it's incredibly flexible. If you need to pivot or add a new idea halfway through, Agile is totally cool with that. You can really see how waterfall builds its structure here. It literally flows downward. You start at requirements, and you absolutely must finish that phase 100% before flowing down into analysis. And then finish analysis completely before design. You get the idea. Now, if your project requirements are perfectly stable from day one, this is beautiful. But what if a client suddenly wants to change a massive feature during the coding phase? Well, good luck trying to swim back up a waterfall, right? That's exactly why Agile, which embraces change and risk in short bursts, has basically taken over for complex, evolving projects today. And finally, let's look at the safety nets keeping the whole operation from crashing down. Section 5, Testing and Documentation, Quality Assurance and Safety Nets.
Get this, 40 to 80%. That is the massive chunk of total project costs dedicated solely to maintaining software after it's already been built. Yeah, the software process definitely doesn't end at launch. The vast majority of the money is spent just keeping the thing running, patching it, and upgrading it as user needs change, which means making your code easy to maintain is quite literally one of the most important parts of the job.
So to make sure the software is maintainable, QA engineers use layers of testing. Think of them like different levels of a security system. First, unit tests. Programmers write these to verify tiny, individual functions all by themselves. Then we zoom out for system tests, checking a whole subsystem at once. Next are regression tests, which I think are brilliant. Basically, they purposely reproduce a known bug and then run repeatedly to guarantee that bug stays dead when new code gets added. And finally, manual QA. This is a real human engineer physically trying out user scenarios to catch all those weird edge case usability issues that a robot script might totally miss. Together, it's an incredibly strong quality shield. But tests alone won't save you. And here is why this matters to you, whether you're coding or just investing in the product. Human memory fades fast. Solid documentation is your ultimate tool for knowledge transfer. We're not just talking about user manuals here, we're talking about writing down the why behind design choices. Like, why did the architect pick this specific database over another? If that's not written down, a new developer joining 2 years later will have literally no clue, and upgrades become a nightmare. Good documentation stops people from reinventing the wheel and keeps those massive maintenance costs way down. So, we've walked through the foundations, the crew, the blueprints, and the safety nets of software engineering. But as we see things like cloud infrastructure and artificial intelligence exploding right now, entirely new roles like AI and platform engineers are already stepping onto the site. The frameworks we talked about today are incredibly solid, but they aren't static. So I'll leave you with this to chew on. With technology evolving at breakneck speed, how will the software engineering process of tomorrow adapt to the wild complexities of AI? How are these invisible